The electronic configurations of the d block elements differ only in the number of electrons in the d orbitals of the penultimate shell, while the number of electrons in the valence shell remains the same. Thus, they have many physical and chemical properties in common. Nearly all the elements exhibit typical metallic properties. Let us review some of them in detail. First, let us look at the metallic character. As the number of valence electrons in these elements is very small, all of them are metals. They are good conductors of heat and electricity. They exhibit metallic luster and are hard. They are malleable and ductile. They form alloys with other metals. They have one or more typical metal lattice structures as shown in the table here. Like beryllium and magnesium, with which they are isostructural, their structures deviate from perfect hexagonal close packing by elongation along the six-fold axis. Mercury is a shiny liquid at ordinary temperature. Melting and boiling points. The melting and boiling points of the transition elements are generally high. The melting points of 3D, 4D and 5D transition metals are depicted in the figure here. As you can see, in any series, with the exception of anomalous values for manganese and technetium, the melting points first increase to a maximum at D5 configuration and then gradually decrease towards the end of the period. The high melting points of these elements are attributed to the participation of a greater number of electrons from n-1 d orbitals in addition to the ns electrons in the interatomic metallic bonding. Now let's look at the atomization enthalpies of these elements. These elements have high enthalpies of atomization. The trends in the enthalpies of atomization of these elements are shown in this graph. From the graph, you can see that they exhibit maxima at about the middle of each series. The maxima in each series indicate that interatomic interactions are stronger in half-filled d orbitals. It means that the greater the number of unpaired electrons, the stronger are the interatomic interactions and the stronger is the bonding between atoms. Consequently, the higher are the enthalpies of atomization. Enthalpy of atomization is an important factor in determining the standard electrode potential of a metal. Hence, metals with high standard electrode potential tend to be noble in their reactions. For example, copper, due to its high enthalpy of atomization, exhibits noble character. You will also note from the graph that the metals of the second and third transition series have greater enthalpies of atomization than the corresponding elements of the first series. This factor accounts for the occurrence of frequent metal-metal bonding in compounds of heavy transition metals.